So we've been constructing gravity as a gauge theory. So let me just do this comparison. What we've been doing is, let's take a look at Yang-Mills on one side and gravity on the other. Basically we start out in Yang-Mills by asking for an invariance. And in Yang-Mills, it's psi goes to psi prime, which is e to the I alpha of x dot tau over 2 psi. This is our u psi. Standard thing. In gravity, it's psi prime is e to the I omega AB SAB over 2 psi, with this is the SAB is minus I sigma AB over 2, if I remember correctly. But we ask for an invariance like that. Now, there is a slight difference. One, in Yang-Mills, you have an internal index, the SU2 index, that psi is a two-component guy. This is within the context of any one fermion. That's the Dirac indices. So it's sort of gauging the Dirac indices. We have new fields then. A mu is AI tau I over 2. Here, A mu is defined as AAB SAB over 2. There's the covariant derivative. D mu minus I G A mu. Here it's d mu plus a mu. So we haven't induced factor G, or basically you could say the coupling constant is defined into the normalization of A. You just absorb it in. The only, I think it's probably more significant that there's no factor of I, but that's what it is. Okay. The transformation is, so A prime mu is u a u minus 1 minus I over G 1 d mu u minus 1. That's the gauge field in matrix notation. Okay, so U is now this matrix. And while I didn't do it this way last time, the matrix notation for the gravitational, the spin connection, is S A mu S minus d mu S minus 1. So it's very similar. S is this spin transformation. S of lambda is e to the minus I omega mu nu sigma mu nu over 4. I guess in my notation here, those should be ABs. And there's an infinitesimal version which we actually worked with. And the field strength then you do d mu commuted with d nu equals minus I G tau F mu nu over 2. And not surprisingly, we do the same thing over here. D mu d nu is S A B R A B over 2. Okay, so on that level, everything is directly parallel. Okay, the place where it breaks apart is the Lagrangian. The Lagrangian in this case is minus a quarter f mu nu. We always do. And here we form, actually what I did forget to say up here, I forgot to mention, we also have the Vierbein field v mu a, which was introduced also. That actually goes into the Lagrangian here. The Lagrangian is a constant. I'll start calling it 2 over kappa squared. I'll tell you a bit more about that in a minute. V mu A, V mu B. Actually, sorry, I forgot my notation up here. I need mu nu down there, of course. Right? I needed that mu nu. R A B mu nu. Okay. This is just our curvature. Okay, so at this stage, everything but that last step is proceeded in parallel, though we could also make this even more in parallel by adding things that look like RAB mu nu, RAB mu nu. Yeah, so let's hold that with some coefficient in front of that. Hold that in the back of our heads for a while, because we'll come back to it. So that would complete the construction on the same level. Okay. So this is what I just described for you is what would be called a first order formalism. Okay. And what that means is that there's two fields, V and R, I mean A, sorry, A. Those are our two fields, and they get connected by the equations of motion, and the equations of motion then for A is A B mu is, if I remember, it was G rho sigma V A rho d by d x mu V B sigma. Okay, so then A now disappears and we only have V, and so first order formalism, this equation of motion is in some sense trivial. It's not a differential equation, it's an identity, right? Normally differential equations you'd have, del squared A is something, so that's a dynamical field. This is not so much dynamical now, it's just eliminated by this first order equation of motion. You can do this also in a second order formulation. And this one is somewhat easier. To do this, let's not do fermions. Let's do a vector particle. Okay, so here we can do things only with G. So this is okay. So the starting point here might be a vector field, some A mu, which transforms a prime mu is lambda mu nu of x, a nu. And to make this work, you then need covariant derivatives on the vector fields. D mu a lambda is d mu a lambda plus some gamma lambda mu nu a nu. So the covariant derivative on a vector field would have that framework, and if you work out, you then have to work out what covariant derivative makes that work. So gamma lambda mu nu is 1/2 g lambda sigma d mu g sigma nu plus d nu g sigma mu minus d sigma g mu nu. This is the affine connection. So this is now our gauge field. Okay, so previously we had the spin connection A, which had these funny indices that were the Lorentz index, Dirac indices A, B, and the Lorentz index mu. So this was gamma A, B, mu. So it was, and that we eventually, after the equations of motion, the affine connection, the spin connection got turned into the affine connection by using the first order equations of motion. This is now our equivalent in the second order formulation. And then you do the same sort of things. You do d mu d nu is something r beta. I'm sorry. I need this to act on something. This acts on A alpha. Is then r beta alpha mu nu A beta. So you just do the commutator. And this then is our curvature. You know, so again, r beta alpha mu nu turns into then d mu gamma beta alpha nu minus d nu gamma beta alpha mu plus gamma lambda gamma beta alpha mu lambda alpha nu lambda mu minus gamma lambda gamma beta alpha mu lambda nu. Okay, so that's the equivalent of the field strength tensor again. So that now everything is not the Dirac indices, but the space-time indices. Okay, and then the construction goes through as before. So, you know, if the world only consisted of bosons, this would be a perfectly good construction. The world does have fermions, so you have to have the spin connection there, and you have so this is a shortcut if you want, without all this Vierbein and spin connection business. But it doesn't save you in the long run, because you need that, because there are fermions existing. So at this stage, we're interested in constructing the gravitational Lagrangian. The Lagrangian actually it can be more complicated than this. At this stage, all we've imposed is the invariance. So we can write, here's the full construction. So there could be a constant, there can be R, the R term, the curvature, there can be R squared, there can be R mu nu, plus higher and higher stuff. Okay. That's the general expansion. What we see from our construction, you can see it right above, is that the nature of what we've just written out here is a derivative expansion. Okay, so gamma goes like the derivative of the metric. So up there you can see the connection going like the derivative of the metric, and the curvature goes like the derivative of gamma or gamma squared, then goes like two derivatives on the metric. And so the Lagrangian that I wrote it there is the derivative expansion at low energies. R squared should be small compared to R because it involves two derivatives. R should be small compared to lambda because it involves two derivatives. Okay? So logic would tell us that we actually keep the constant. Let me actually just put a square root of g out in front there to remind you that even the first term has some dynamics associated with it. So let's for the moment postpone these guys. I'll come back to them quickly. And keep the first term. Okay, with the first term you get Einstein equation. You get R mu nu minus 1/2 G mu nu R plus this guy is it's actually minus 8 pi G lambda equals minus 8 pi G T mu nu, where this is the energy momentum tensor for the rest of the stuff. Okay, I've actually used implicitly here that kappa squared is defined is 32 pi G, where G is the Newtonian gravitational constant, right? Okay, so this is your cosmological constant. Lambda is 8 pi G, big lambda. And depends which one you see quoted. This one is of order, what is it? It's of order 10 to the minus 56 centimeters. This big lambda is of order 10 to the minus 46 GeV to the fourth. So there's different units, but there we go. Okay. So the first order of business of this effective field theory seems to fail in a way. We expect this term to be small compared to the cosmological constant. It isn't the cosmological constant small compared to the curvature. Okay. Okay, so let's drop that for the moment, and we can of course come back to it if you want. But if I will drop that for here. Then let's look at the curvature piece. For the curvature, we're going to expand G mu nu is eta mu nu. Actually, let me do it completely right. We eta mu nu plus h mu nu. Okay, that's going to be our definition of our gravitational field. And actually, I want to put kappa here. Kappa there, okay? That goes into this normalization here. The G lower, then, is the inverse of that. Eta mu nu minus kappa h mu nu. Plus 1/2 h lambda mu h lambda nu plus dot dot dot. So technically we can, and there's kappa squared there of course. Technically we can make the top definition exact if you want. The top definition doesn't have to imply that h is small, it could be big. But the second part does imply that h is small, because G lower has to be the inverse of G upper, and so this term only works to order h squared. So you have to be careful about the expansion that you do there. Okay, if you do this, then R starts out with the term kappa box h lambda lambda minus d nu h mu nu. So there's the two derivatives. And then there's of order h squared in order h cubed plus dot 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 h to the fourth, etc. The h squared piece was in your homework. That's the term, if I multiply by 2 over kappa squared, that I wrote into your homework. So you've seen that guy exactly. This is the first order term, and then R mu nu, which enters Einstein's equation, is well, it's kappa. I'll write it out. It's got a lot of terms, but d mu d nu h lambda lambda d lambda h mu nu minus cross terms d mu d lambda h lambda nu minus d nu d lambda h lambda mu. Okay. So then there's higher order pieces there also. Okay. So Einstein's equation that's set up there has R and R mu nu in it. So let's just rewrite that first order equation in terms of these guys. Yeah, it actually it looks complicated with all these terms here. At this stage, it's good to do gauge choice. Harmonic gauge is h mu. The derivative lambda h mu lambda is 1/2 the derivative mu h lambda lambda. Okay, so that's harmonic. Then the equations of motion reduced to box h mu nu is minus 16 pi g t mu nu minus 1/2 eta mu nu t lambda lambda, the trace. And this then gives us our gravitational field. It gives you gravity waves. This guy, if you set the sources equal to 0, there's gravity waves. And gravitational field. And all the good stuff that you did in homework. Okay. The other thing that comes out of this at this stage is an important thing in thinking of the phenomenology of general relativity is that if you have non-relativistic matter, the mass enters, so it's basically T00 is the only energy momentum piece. There's a T00 here, and then there's a trace gives you something, so you have the 00 and the eta mu nu piece there. If you're, however, doing the bending of starlight, has T mu non-zero, but it's traceless. The energy momentum tensor for photons is traceless, so you only get the first piece. So part of the phenomenology of general relativity is that distinction. Okay. Okay. Let's come back to the next order terms, the r squared terms. Okay. And let's not pay too much attention to the details. The details have been worked out by Stelly in a classic paper where I can always get you the reference on that. But the Lagrangian now is this 2 over kappa squared r plus c, some constant times r squared. If you look at the dimensionality of this constant is dimensionless. This constant here, 2 over kappa squared, goes like a mass squared, because you've got two derivatives there. The metric is dimensionless, so it's just the derivatives that you count. So the one has two derivatives, so it's dimension mass squared. This is the Planck mass squared is the coefficient of the first one, and the second one has a dimensionless coefficient. Okay. The first one starts off with two derivatives h. This thing turns, then there's that thing squared. So you can then see that the equations of motion then have the following form. You end up with box h plus kappa squared c box h is 8 pi gt. And kappa squared then is also of order g. Okay. So if you solve this, you would solve this by a Green's function. The Green's function is then integral d for q over 2 pi to the fourth e to the I q dot x over, q squared plus kappa squared c q to the fourth. That's what you do. You would take this guy, so this is equals dot dot dot. And you can look at this as using partial fractions. So if I separate that by partial fractions, I get this piece. Now, if you're just following it along, you can see 1 over kappa squared c is of order m Planck squared over whatever that number is, c. So our immediate thing would be to approximate that by a delta function. Okay, so you end up with v of r. Actually, there's two things you could do. One is we know how to we also know how to solve this with a particle of any general mass like that. That it's a Yukawa. So one way to do it is to write this v of r would be something that looks like g m 1 over r from the first piece, that's the usual gravitational piece, minus e to the minus r over kappa squared c, that over r, that's the Yukawa piece, that's the second term. Okay. In this form, there is some promise that people were interested in it for a long time, in that one of the things that this has is that as r goes to 0, this is less singular than a Coulomb potential. Okay. Likewise, that's equivalent to saying as q goes to gets very large, the propagator is more suppressed than the usual propagators. That was a hope then, that by doing this, adding these terms, you can make the quantum theory better behave. The quantum theory of general relativity, which we'll see a bit, has bad divergences in it. And so by killing the propagators at large momentum, there was thought that you could solve things. And that's the equivalent of short distance. So this cancellation at the origin is always there. It's not just an approximation of me dropping indices. It's always there. It's just basically that this falls faster than 1 over q squared at high momentum. But it doesn't save you. It doesn't save you. Okay. The other way you could write this is the way that we would write it, is g m over r minus a delta function term, which actually turns out into be if I did it right, it's 128 pi squared g squared m delta 3 of x. Okay. So there's very little we can really say about that extra piece there. It's if c is of order 1, is dimensionless, so that's the natural assumption, then this square root of kappa squared c is 10 to the minus 35 meters. Centimeters? Meters. Okay, so 10 to the minus 20 of a Fermi, which is the size of a proton. So we've never tested anything of order that scale. That's the Planck scale, Planck distance. So we would never have seen that Yukawa, or equivalently, we don't see the delta function. Okay. So there's essentially no constraints on this. You know, what Stelly did is he bounds this thing. He says, well, if C is of order much bigger than that, then maybe we could see it. And what's the limit on it? And the limit turns that C is less than 10 to the 74. Okay, so in other words, we're completely insensitive to C. C of any dimensionless number less than 10 to the 74 we would never see. Okay. Questions about that stage? Okay. So let's do background field quantization. Okay. And the idea of this is it's a way where we can retain the symmetries of general relativity and yet do the quantization. So here, the idea of a background field is that you take this metric, g mu nu, it's a function of x, and you don't expand it around flat space like we just did. The previous expansion was about flat space, but we expanded about a general background field, some curved space. And again, those really should be uppers, but forget that here. Then you expand the action 2 over kappa squared square root of g r is square root of g bar 2 over kappa squared r bar, well, that's formed by the background curvature. That's just a constant. And then there's terms, the first order plus terms of second order, etc. Okay. At first order, my first order is 1 over kappa h mu nu g mu nu r bar minus 2 r mu nu. Okay. As always, when you get the first order term, this goes to 0 by the equations of motion. Okay, remember that was the equations of motion. That's Einstein's equation sitting in the square brackets. And anytime you have a first order variation, if the background satisfies Einstein's equations, the first order variation vanishes because that's how you get the equations. Okay, so that's bar, yes, thank you, yes. Yes. Then the second order term, there's a bunch of terms, I won't write them all out, but it starts off with the kinetic energy pieces, d alpha h mu nu, d alpha h mu nu. Everything's raised and lowered by g bar now. And the covariant derivatives carry spin connections of affine connections of g bar. Okay. And as you go out here, then there are other terms too. Let's just write out one of them. You know, there's a r bar mu nu times h lambda lambda h mu nu. Okay, plus lots of other terms. Okay. This is going to get put into, we have a little bit of work to do before we get there, but this will be some h alpha beta d alpha beta mu nu h mu nu. It's some quadratic form that it's like our heat kernel, a little heat kernel thing. It has two derivatives, d squared. It has gamma times d, and it has the sigma term. So actually, let's just write it out. It looks like d plus gamma squared plus sigma, where you just collect terms. So here's a term that it goes into the sigma piece. You know, here's 1h in our bar, so there's some constant piece that looks like that. Okay, so we're almost there. However, you can't at this stage. This is not invertible for the same reason the gauge theory is not invertible, is the inverse of the propagator doesn't exist in this case. So you have to do gauge fixing. Okay, and the gauge constraint for harmonic gauge is the following. G A is the fourth root of G d nu h mu nu minus 1/2 d mu h lambda lambda times v mu a. Here's our Vierbein field. Okay. And so then gauge fixing is the gauge fixing Lagrangian is GA. So that's that constraint squared. So this is like our gauge theory construction, where we had the gauge constraint for d mu a mu, and you put it in there squared into the Lagrangian, and then so this adds into the Lagrangian, and then this piece is also of order h squared, and it goes into this d alpha beta mu nu term, so it gets fed into that. Okay, so it's another piece of that in addition to the other. Then it turns out that it's invertible. Okay. However, we know that when we do this gauge fixing piece, there's this extra term in the action, which comes from the determinant of G A with respect to the gauge transformation, which let me call epsilon here, epsilon B. That determinant lives in the path integral. And the way we get rid of it is these Faddeev-Popov ghosts. So we exponentiate if you remember the trick, determinant of this m is integral d eta bar, fermion fields, e to the I integral d for x eta m eta. So what we have to do is we have to calculate then what's the, I'm going to do this quick. I have the whole calculation worked out here in case you ever want to see the whole bloody thing. But basically you have to calculate what the variation of that gauge fixing term is with respect to a gauge transformation. The gauge transformation is h mu nu goes to h prime mu nu plus d mu epsilon plus nu d nu epsilon mu, which you saw in your homeworks. Okay, so you just basically you take that gauge fixing term, you do this transformation, and so there's terms involving epsilons, and then you take this variation and you get it out. Then this tells us that dg alpha d epsilon dga epsilon b is the fourth root of g there's a delta a b d nu plus d nu commuted with d mu, no, d b commuted with d mu Vierbein mu alpha mu a. Anyway, this ends up then with a ghost Lagrangian, ghost fields. They actually live in this Vierbein space, so eta a, and they're Fermat fields, and the ghost Lagrangian is square root of g eta star mu d mu d nu g bar mu alpha minus r mu alpha eta alpha. So there we are. There it is, because we've converted them back to. Okay. So the total Lagrangian then, at this stage, we have f is integral d for x square root of g bar is 2 over kappa squared r bar plus h d alpha beta mu nu h mu nu plus this this eta term that we just wrote out there. So let's not bother writing that out. Okay. Okay, so there's quantization of the thing. We can do renormalization also. Okay. In fact, we could almost do it out. I don't have it prepped for this, but it does involve a lot of algebra. But basically, the trick to doing it is we do the heat kernel method. So we've got this. The basic term is the h term. We have the expansion of that in terms of derivatives and gammas and all that stuff. And you turn the crank and you get the result. And it's first gotten by Tust and Veltman. And let me just give you the answer. The answer is nice and simple. Where is it? Where is it? There we go. The divergent piece in the Lagrangian is 1 over 8 pi squared epsilon 1 over 120 r bar squared plus 7 over 20 r mu nu bar r mu nu bar. Okay. So the features you see about this is that this term does respect the background symmetries, respects the so that's the beauty of the background field method. This is actually much more painful if you didn't use the background field method. This is one of these where background field plus heat kernel is a tremendous simplification. If you ever try writing out those Feynman rules and doing this by the old-fashioned way, it's extremely painful. Okay, this tells us that we renormalize. We take C1, renormalize to C1 plus 1 over 960 pi squared epsilon. C2 then is C2 plus 7 over 160 pi squared epsilon. And once you've done that, all your divergences have gone, so you've renormalized the theory. You at this stage see what was at one stage a famous theorem, which is that pure gravity is one loop finite. Okay. And the logic of that statement is, so we've gotten these terms from in this Lagrangian, but the pure gravity equations of motion are r mu nu equals 0. Okay, it's actually r mu nu minus a quarter g mu nu r is equal to 0, but both of them have to be equal to 0 then. Both r and r mu nu have to be equal to 0 in pure gravity. Okay, which means that these counter terms here vanish. These terms here vanish by the equations of motion, so they actually don't contribute to anything. And so everything that you get out of pure gravity has no divergences at one loop. It didn't have to work out that way. This is actually only in 4D. There's another invariant which we didn't write out, which is r mu nu alpha beta, r mu nu alpha beta. Which doesn't vanish. So the 4-index curvature doesn't vanish in pure gravity, but that combination can be written. I'm not sure if I have the identity here. Maybe I do. But anyhow, it can be written as a combination of r mu nu plus r terms, r squared terms. So there's some identity that in 4 dimensions reduces this down to that. Okay. So that's that tells you that it's one loop finite. It's not two loop finite. It fails at two loops. There's a R mu nu alpha beta, R alpha beta gamma delta, R gamma delta mu nu. That's not equal to 0. That counter term and explicit calculation shows there's a divergence in front of it. Okay, so that's not true. And it's also not true, it's not finite when you put matter in, because then the equations of motion give you something that's non-zero, and so these divergences stay there. So it's a classic result, but it's not. Yeah. Okay. So if I've quantized it, I can then write out Feynman rules. Okay. The usual things that you do is you write the propagator. The propagator goes like I over q squared plus I epsilon times some p mu nu alpha beta, and p mu nu, so this polarization guy, so this mu nu here, alpha beta coming out there. P mu nu alpha beta is 1/2, it's okay, this is around flat space, eta mu alpha eta nu beta plus eta mu beta eta nu alpha minus eta mu nu eta alpha beta. Okay, you couple up, that's the propagator. You couple up the graviton to the one I'll write out is the scalar here, so it's p. This is some vertex tau mu nu, which is minus I kappa over 2 p mu p nu plus p prime mu p nu minus g mu nu p dot p prime minus m squared. Okay, that's the energy momentum tensor, matrix element for that guy. There's couplings that look like this, two gravitons, which I won't write out. There's couplings that look like that and like that, which I won't write out. If you've ever seen me give a talk on this, you realize that this guy takes up a whole page of paper, a whole page. And I've never written that one out explicitly myself anyhow, so okay, it's just too long. Okay, and then usual things happen. You know, if you do a calculation, you do that exchange. That's the tau mu nu 1 over q squared minus I tau mu nu I over q squared p mu nu alpha beta tau alpha beta for the lower vertex. Okay. That gives you, the full relativistic form looks complicated, but this turns into something that goes like in the non-relativistic limit, G M1 M2 1 over Q squared, and there's a 4 pi there. So this Fourier transforms into a potential GM1 M2 over R if you Fourier transform it. So that gives you your usual stuff. Okay. The further calculations, let's take graviton scattering. This is an exercise to do this in standard notation. It's extremely painful. There's that vertex there. We can do that vertex, okay? But there's also vertices that look like this, plus vertices that look like that, and the other one is the cross one. That's it. Okay, the cross one. And it turns out that there's incredible cancellations among those. And I don't know, I've actually never sat there, but the answer turns out to be actually remarkably simple. It's sort of funny. If you project on physical polarization, so of course one of the things I didn't explain is there's only two polarizations of the graviton external fields, which are the helicity +2 and -2. So I didn't go through that part. But if I take the amplitude for helicity plus going to plus, or the amplitude for minus going to minus, that actually has a very simple form. It goes like kappa squared S cubed over STU. Okay, and putting it in a particular funny form, but S clearly S squared. And so you go through all this incredible algebra with all those terms, and that's your answer. It's really funny. It really makes me believe that there's a better framework than this, than the one we're doing. There's some sense, some of these advanced helicity-based techniques that have come with the so-called twister theory make some of these calculations easier. But I've never reformulated the whole of general relativity using those. So that's interesting. That comes out that easily. And then, of course, you've probably heard some stuff about loops there. If we do loop calculations where we take diagrams like that, plus diagrams like this, plus diagrams like this, plus diagrams like that, plus diagrams like this, and work out all the, I guess I forgot the cross boxed. I think I've got the whole set of diagrams then, okay? So this is doing scattering of two particles. This is one of these calculations that I'm quite proud of. This gives you the next one loop corrections. It's perfectly finite. There's no I can explain that. I guess I'm not going to have time. But you end up with a V of R is GM1 m2 over r. 1 plus, the answer is 3g m1 plus m2 over r plus 41 over 10 pi g over r squared. Okay, if you put h bars back in, the h bar sits there, so there's the quantum effect. This is a classical nonlinearity, which you can get equivalently by doing the classical post-Newtonian approximation. So in a Hamiltonian formulation. Okay, post-Newtonian is the first order correction after the Newtonian limit, which is the one I showed you before. Okay. So that's the nature of the quantum theory. The energy expansion that we have done is, well, we've sort of seen the nature of the energy expansion. You can see it right there. In momentum space, any matrix element that's a function of the momentum would go like, some lowest order matrix element. Then there'd be 1 plus corrections of order GQ squared. There'd be corrections over G Q squared log of Q squared. And actually those terms come from the log, actually. I haven't had a chance to explain that, but then plus, 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 plus. So that you see a couple things. Is your quantum corrections get big at Q squared is 1 over G, which is m Planck squared. Okay, so the theory tells you that it breaks down quantum breaks down at the Planck scale. And there's really nothing that at least in perturbation theory, we can do about it. So this is the problem of quantum gravity. So the low energy theory is fine. It's fine. So that already tells you that many of the things you read about quantum gravity are wrong. The things that say that quantum mechanics and gravity don't go together. We've just outlined how they go together just perfectly, just like any gauge theory. But the high energy theory breaks down is not so fine. Okay. Now we had some breakdown even in QED. Remember when we had the running coupling constant? There was this Landau pole in the running coupling constant that blew up at some ungodly scale. That's way up there. That has a chance of being solved by non-perturbative effects. We don't really know much about it, but it's so far away that we don't worry about it at all. This is a little more worrisome, and there's a lot of puzzles that come out of quantum general relativity. that they all come, as far as I can see, they all come from the Planck scale physics. And this breakdown is not logarithmic, it's power law, so it seems to be significantly worse. So we do have the expectation that then there's something going to happen at the Planck scale. The Planck scale is clearly signaled out for us just by the low energy theory by itself. It points to the place where it breaks down. So whether it's strings or whatever it is, something else can happen at that scale. All right, let me finish the course right there. You write QED at the bottom, but it's QFT. There we go. Okay, good, thanks. Thanks, guys.